Measures of variation part 2. We did that first part just to kind of get used to how that calculation would work, and we talked a little bit about what it meant, but today we're going to go into more detail. Let's start with some questions. The ages of 300 students in a high school were compiled. Given that the population variance is 10.9 and the population standard deviation is 3.3, what are the units of these measurements? So I just wanted to touch on the fact that these units, for example, the standard deviation is going to be measured in the same units that your data was measured in. So since we were talking about ages, we would be talking about how many years old someone is. And technically, when we square that, it winds up as years squared, which doesn't make quite as much sense, but we're talking about distance from the mean, remember. And so this one is the average distance from the mean squared, and you can think of this one as an average distance from the mean. If you were to choose a sample of 10 students from the same high school, give an example of how you may get a statistic of S equals 0. So we know that the population standard deviation is 3.3. But when we choose a sample, is it possible that the standard deviation could be 0? What that should tell you is that you think of it as a spread, that those ages would not be spread out at all. So maybe we sampled 10 people who were all 16, all the same age. Since there's no spread at all, would give us a standard deviation of 0. How about this one? How would you choose 10 students if you wanted the highest standard deviation possible? How would we find the biggest variety, the biggest spread from our ages? I would try to find the youngest and the oldest people in the school. So how young are freshmen? Maybe 14. I don't know if maybe you could find a 13-year-old down there. But if you chose some that were very young and some that were very old, maybe we even have a 19-year-old. If you chose those, that would be very spread out and would give us a high standard deviation. This is just kind of a fun exercise. We've got set 1 and set 2 of numbers, and we're just going to decide where these numbers over here fit into each of those values without doing any major calculations. You shouldn't need a calculator for this. N stands for how many data values there are. In set 1, I count 8 data values, and in set 2, I believe there are 10 data values. What's another one to easily calculate? The range. The range would be the highest minus the lowest, so 29 minus 20. On the bottom one, 100 minus 1. Easy, easy. Let's find those medians. For set 1, where would we be? Right in the middle here, so 25. And the median on the bottom set, what's halfway between 39 and 48? Add them together, divide by 2, 43.5. All right, now it's going to start getting tricky because I'm a little too lazy to add all those numbers and divide by 8, or add all those numbers and divide by 10. So maybe we can just use our reasoning here to figure out the rest of these numbers. The first thing I noticed is that, you know how there's an S squared and an S? Maybe we could decide which of these are squares of each other. 30 squared is 900, so maybe those go together. Do you suppose 3.5 squared is pretty close to 12? So maybe these are our other guys. So I think that this is going to be an S squared versus an S, and here's another S squared versus an S. So X bar, do you think this is the average of the top, or do you think this is the average of the top? I would say this one on the bottom. That would make sense for the average. And I say average, but I meant mean, right? All right, now which of these data sets is more spread out? I would say set 2 is more spread out, so we should expect it to have a higher standard deviation. When it's more spread out, we get higher standard deviation and variance, and when it's not as spread out from the mean, we get those lower values. I'm going to teach you a quick little formula called coefficient of variation, which is used to describe sets of data that maybe are measured in different units, maybe degrees Celsius versus degrees Fahrenheit, so we can compare them better, or maybe birth weights of baby animals. It's hard to compare an elephant to a hedgehog, but coefficient of variation is a way to do this. The mean July high in Winnipeg was 26 degrees Celsius with a standard deviation of 2.8 degrees Celsius. The mean July high in Fargo was 82 with a standard deviation of 5.5, and that's in Fahrenheit, which temperatures varied more. And so normally, if I asked which ones varied more, I would look at those two standard deviations, and whichever one was higher, I would say that one varied more. But in this case, we're using different units, and so the coefficient of variation is the way to figure this out. So let's calculate a coefficient of variation for Winnipeg. What we're going to do is we're going to take S, the standard deviation, divided by X bar, which is the mean, times 100. And that just puts it in a percent for us. And then for Fargo, same thing. Only 5.5 for standard deviation and 82 for the average high. So for Winnipeg, that comes out to, I'll say 10.8% coefficient of variation, and for Fargo, 6.7%. So it turns out, if we were all measuring in the same scale, it would have been Winnipeg that had the higher variation, temperatures that varied more. So again, coefficient of variation is just a way of looking at standard deviation for two different sets that aren't measuring in quite the same way. We know that standard deviation describes how spread out the data is, but here's a theorem called Chebyshev's theorem that really gives us a feel for where the data are located. And so, named after Pafnuty, the Chebyshev's theorem says that for any data set, and that's actually really surprising because we don't know how this data is distributed, but all you need to know is what the standard deviation and the mean are, and you can locate 75% of the numbers, 88.9% of the numbers, 93.8% of the numbers without even knowing what the original data was. Here's an example. On the Chapter 2 stats test, we had a class mean of 80% and a standard deviation of 13.3%. We know that at least 75% of the scores were between, and normally you would say, I have no idea what the range is. I have no idea what the data values are. All I know is that class average, the class mean, and the spread, the standard deviation. But here's how Chebyshev helps us out. We can take that 80, which is the middle number, and we can add, did you see it said 2 standard deviations from the mean? We can add 2 13.3s to that. And that gives us 106.6. We also want to go in the other direction, so we'll take that mean and we'll subtract 2 standard deviations, which gives us 53.4. So that is an interval that we know that at least 75% of the scores are between 53.4, and these were measured in percent, and 106.6. If there was extra credit, maybe we'd have them in there. But I just think that's amazing. You can tell that at least 75% of the students are between there and there. And we could make that even stronger. We could find more and more of the students in intervals just by increasing the number of standard deviations away from the mean that we go. If you were not a fan of filling out those tables before, remember when we did standard deviation using the table, x minus x bar, square them, add them? These formulas actually give you the exact same answer, and to me they even look a little more complicated, but they call them the computation formulas because they're easier to compute actually, and we'll see that when we do some examples from our homework. And if you're still with me, would you like to do problem number 13 from your homework together? Part A says to find the range. You know, I think I would probably just put these in order first, just to make things easier on myself. So to find the range, we take high minus low. I'm getting 15. For part B, it asked us to verify the sums. And so we were supposed to verify the sum of x squared and the sum of x. And so the sum of x, we're pretty familiar with that. That's just where we add up all the data values. But the sum of x squared is where we add up the squares of all of those values. So when it asked us to verify, we were just checking their numbers that they gave us from the book. Now we're going to try using that computation formula for the first time to find s and s squared. So the standard deviation is equal to the square root of the sum of x squared, which is 2,568, minus the sum of x squared divided by n. We've got 5 numbers here, and all divided by n minus 1. So that's why the computation is just a little easier on this formula, because we didn't have to make any of those crazy tables. You'll want to be a little careful typing that in. Probably type in just the top stuff first. Ease into it slowly. Comes out to the square root of 37, which is about 6.1. So we could say that s is 6.1, and then s squared, the variance, would be that 37. Part D has us compare that method to using those defining formulas. So the defining formulas are where we had to do the table. So first we'd need to find the mean. Thankfully, I already know that when I add those up, I get 110. 110 divided by 5 gives us a mean of 22. So I'll be subtracting 22 from each of those values, and then squaring them. And then adding all those together. So that was the background work on there. And then remember, standard deviation, we just took the square root of that number divided by n minus 1, and you'll notice that we're getting the exact same calculation right here. So 2 different ways to calculate those same values. And then finally, part E, if the data was population data, if we knew that these were all of the data in the entire population, what would change? And the thing that changes, if you compare the formulas, the only thing that changes is that n. The n is capital because it's population now, but on the bottom we don't divide by n minus 1, we divide by just n. So the only thing that's going to be different for the population standard deviation is that we'll take that 148 and divide by 5, not 5 minus 1.